All right, so this is on the board from chemistry class. Let's just see if y'all remember how to do this. You need to know it. It's probably too simple for an AP question, but you never know. That might be something like that. So these are three isotopes of argon. Okay. So if you remember from last year, an isotope, two atoms that have the same number of protons but different number of neutrons. Right. So the same element, they have different masses. There's one weighs more than the other. Okay. So we can figure that out. We're just given this symbol right here. We should be able to determine these three numbers with this symbol in a periodic table. So if you find argon on the periodic table, it's number 18. So that's your protons, right? Since there's no symbol up here, it's neutral, so there's 18 electrons. Okay. And since it has a mass number of 36, 36 minus 18 means there's 18 neutrons. So that's the protons plus the neutrons. Okay. So argon 38, 18 and 18, but we got 20 neutrons now. So 18, and argon 40's got 22 neutrons. So these three atoms are the same except for the mass, because we got a couple extra neutrons. Okay. Same thing's happening here. A little bit different here is we have a charge, right? So calcium's number 20. Calcium 40 means it's got 20 neutrons, because 20 plus 20 is 40. 2 plus means it's got a deficit of 2 electrons, so it only has 18. Phosphorus 3 minus would be 15. With 18 electrons, 31 means it has 16 neutrons. Okay, you remember how to do that, right? That's good. Probably not an AP question, but maybe somehow kind of is. I don't know. You never know how they come up with stuff. Okay. I got your periodic tables in front of you. Prior as it goes there. All right, so periodic table, okay. So we're going to talk about what we call periodic trends. So remember that a trend is not an absolute, right? Correct? A trend is just sort of kind of the way it works. Right? It's not absolutely perfectly the way it works, but it's sort of the way it works. All right, let's start with atomic radius. First thing, so we're going to learn all these little things in 2 parts. Okay, we're going to learn the trend on the periodic table, and then most importantly, we may not have done this last year. In fact, last year we did a poster on this stuff, didn't we? Yes, we didn't do this. Okay. Yeah, we got this is what we kind of ran out of time. All right, so we're going to learn the trend itself. All right, and some of these we'll have to learn some exceptions to the trend. But then most importantly for AP level is we've got to learn how to explain the trend. Okay, so why is it that way? All right, we would not have done that last year. Problem. Okay, so atomic radius. Okay, the trend, all right, is that radii increase down a group, and decrease across the period. No exceptions. Okay, so what we're saying is that within any group, take the first group for example, the atoms get larger going down the group. Okay? Going down the group, atoms get larger, going across a period, they get smaller. That should seem a little counterintuitive. Okay, let's talk about the one that should probably make sense to start with. So why? Well, there's two whys. One is for the within groups trend. Okay, it's because of increasing energy levels. Which equal orbital size. Okay, so a 2s orbital is larger than a 1s orbital. So let's go back and redefine what an orbital is. It's the region of 90% probability that holds an electron, right? Okay, so if we take sodium, for example, okay, sodium has 10 electrons, 11 electrons, right? 11 electrons, okay? And they all are located, what's that? Huh? Right here? Increasing. Okay. So these 11 electrons all have an orbital that they occupy, okay, which is a region of space that there's a 90% chance that electron is actually in there. 10% chance it's not. Okay. We can't know anything for sure when it gets down to quantum level stuff. Okay. The shapes of those orbitals are based on whether it's S, a P, a D, or an F. The energy is based off that principal quantum number, the 1, the 2, or the 3, right? Well, a 2s is bigger than a 1s. So in other words, these two electrons are in a 1s orbital, which is a spherical shaped region. It's like a ball. These two electrons are in a 2s that has the same shape, but is larger. Okay? So these have the potential, or on average, will be further away from the nucleus than these would. Okay? All right? This electron will be, on average, even further away from the nucleus. Now, that electron might be anywhere from inside the nucleus to out to wherever the boundary of that region is. But the boundary of this electron is much further out than the boundary of this one. Okay? So on the average, this electron is further from the nucleus than this one, which is further than this one. Okay? So as you increase energy levels, things get larger. All right? In comparison to, let's say, potassium, okay, which is 1s, 2s, 2p, 3s, 3p, 4s, potassium is larger. Okay, now, here's what you cannot say on the AP exam. Okay, the question will be, statement won't be a question actually, it's a statement. They're going to give you a statement of fact and ask you to explain it. Okay, So they're going to say potassium is larger than sodium. Explain. Okay? Here's what you cannot say. You cannot say potassium is below sodium on the periodic table. Okay, that's called an observation, not an explanation. So you have to give an opposite explanation. Sorry, you have to give an explanation based off the atomic structure of the two elements in question. Okay. So the explanation is based off structure is sodium's valence electron, outermost electron, is in the third energy level. Potassium's outermost electron is in the fourth energy level. Fourth energy level is larger than the third. So it's a couple of three sentences. Okay. Everybody might word that a little bit different. But do not make any mention of locations on the periodic table. They're going to automatically count the whole thing wrong. Okay. Because they don't want to hear that. Because that's not a chemical explanation. The periodic table is this little man-made chart that some Russian dude in 1860 something came up with just to help us keep up with stuff. Okay, it's not the physical chemical reason for why things are the way they are. So we want the physical or chemical reason that potassium is bigger than sodium.
You said you would write that how?
How?
Yeah, like you said that, like you'd have to say like.
You got to tell them about both substances, something about the atomic structure of both substances. How that affects what they're telling you. Okay. So they're going to just give you this statement: potassium is bigger than sodium. Period. Explain. Period. Okay. It's not more so much a question as it is a task. Right. So you're going to say, well, sodium's got a valence electron on the fourth energy level. Sodium's got one on the third energy level. Fourth energy level is larger than the third. Don't tell them 4 is bigger than 3. They know that. Kindergarten, right? The fourth energy level is larger size than the third energy level. That's chemistry, not kindergarten math. That 4 is bigger than 3. A lot of people say that 4 is bigger than 3. True, but what does that mean chemically, right? Okay. So that trend holds up for every group without any exceptions. So that explanation holds up for every group. So they could give you 10 is bigger than germanium, okay, or radon is bigger than xenon, or whatever, right? Okay. And within that group, it's always going to be the case that this is radon is bigger than xenon because its valence electrons are on the 6th energy level, and this one's are on the 5th energy level. The 6th energy level is larger than the 5th. Okay. Pretty simple. Maybe. Okay. It's require writing a sentence to agree. Okay. All right. Now we get maybe a little confusing. All right, within periods, the explanation has to do with, that'd be great, I'm going to do last. Effective nuclear charge. Okay. This has a symbol, ZEFF. Z, for some reason, and I don't know why, is the symbol for atomic number. That seems like about the worst letter. Something starts with an A, symbolized by Z. But anyway, Z symbol, capital Z is a symbol for atomic number. This little subscripted EFF stands for effective. Okay? So it's the effective nuclear charge. Effective at doing what? Holding electrons. Okay? All right, so that's what we're effective at doing. Is how effective is the nucleus at holding electrons? Okay. Now, if you're going across a group, let's just take carbon and nitrogen, for example. Okay. Carbon has an atomic number of 6, nitrogen is 7. You would think, by looking at that, that nitrogen would be larger. It's got more stuff, right? So when we think of macroscopic objects, Newtonian physics, more means bigger, right? Okay. If I had more people in this room would weigh more, right? That's just kind of the way our brains are wired. Our brains are not really wired to think of things the way things are at the atomic level. Okay, we really have to be careful about what we just assume to be true. Okay, we're dealing with these atoms. So what happens here is we have to remember one thing that you always have to remember is that electrons are extremely tiny. Okay, extremely tiny. They have mass, but it's not enough to even hardly matter. In fact, when we figure the mass of an atom, we don't even add the electrons. It's protons and neutrons. You can add up the electrons, and then you round it back to significant figures, and they disappear again. Okay, they're so small that they're insignificant in terms of mass. But they are extremely significant in terms of positive and negative attractions, negative and negative repulsions. Okay, so the world of the electron is more about its ability to attract and repel stuff than it is to take up actual physical space. Okay, so what's going on here is 6 protons are pulling on 6 electrons. Okay. When you go to nitrogen, which is one step to the right, you've got 7 protons pulling on 7 electrons. Even though that's more stuff, it's a smaller atom because the attraction is greater. 7 and 7 pull harder than 6 on 6. Okay, so this is carbon with 6 pulling on 6. When you go to nitrogen, 7 pulls on 7 a little more and it shrinks. When you go to oxygen, it shrinks again. And fluorine shrinks again. And neon shrinks again. Okay, because of the effective nuclear charge of the atom. That's the phrase that they're looking for. So on several of these trends that we're going to talk about, when we're dealing with things across a period, across a row of the table, your argument or your explanation needs to be based around effective nuclear charge. They're going to be looking for that phrase, your statement. Okay? So, if they said on the AP exam, carbon is larger than nitrogen, explain. Okay? Explanation is that nitrogen's 7 protons give it a greater effective nuclear charge than carbon's 6 electrons. Therefore, nitrogen will be smaller because of the greater effective nuclear charge, because of that pool of protons and electrons. Okay? How are we doing? All right. All right. Next one is ionization energy. Here we're going to have exceptions. That's where it gets real fun. Should have used nitrogen and oxygen as my example. I wouldn't have to erase it. Then I got to put a different one up here too, so let me just place it. All right, so here we go. Ionization energy. What does that even mean? Let's see. It's the energy required to remove an electron from an atom. Okay. trend is going to decrease down a group. So ionization energy decreases going down a group. This is often abbreviated IE, by the way. It's going to increase across a period. This trend has exceptions. Here are the exceptions, there's two of them. If you're going across the period, there's an exception from group 2 to 3. From group 15 to 16. What do we mean by exceptions? That means that it's increasing to go across the period, except when you go from group 2 to group 3, then it dips a little bit. Okay? So beryllium has a higher ionization energy than lithium does. Okay? But boron has a slightly lower ionization energy than beryllium does. Carbon is larger than borons. Nitrogen is bigger than carbon. And oxygen is a little less than nitrogen. And then fluorine is bigger than oxygen, and neon is bigger than fluorine. So it generally increases, but there's two places that it dips. Increases, decreases, increases, increases, decreases, increases, decreases. Okay. I'll explain why.
Can you say that again? One more time.
Increase, beryllium is higher than lithium, as the trend says it should be. Okay. All right. But boron is lower than beryllium. It dips instead of goes up. Then it goes back up to carbon, back up with nitrogen, dips a little bit with oxygen, back up with fluorine, up to neon. Find a picture of the actual numbers. That's what I'm getting to in just a second. Hang on, let me see if I can find a picture of the actual numbers. Somewhere I'm getting it. I think maybe in the textbook.
Mr. Cable,
Uh-huh.
why does it dip going from beryllium?
I'm getting there in just a minute. We ain't got to that yet. Okay. Here's the numbers for the third period on the table. So this is sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Okay. So 495. It takes 495 kilojoules of energy to take away the outermost electron of a mole of sodium atoms. That's what that means. Okay. So if I got a mole of sodium atoms, which would have a mass of how many grams, by the way? Drag stoichiometry into this wonderful conversation. But had a mole of sodium atoms, how much would they weigh? On the periodic table. 22.99 grams, right? Yep. So if I had 22.99 grams of pure sodium, okay, laying in my hand back here, okay, and we wanted to take all of its valence electrons off, that would be 1 mole of valence electrons that we had to remove, right? And Avogadro's number of valence electrons, we got to kick off some atoms. It's going to take 495 kilojoules of energy to do that. Okay. Energy required to remove an electron from an atom, right? Okay. If I want to take 1 electron off of magnesium, it takes 735 kilojoules. It takes more of it, right? So its ionization energy is higher. When I go to aluminum, it drops to 580. There's a dip between group 2 and group 3. Okay. In silicon, 780, phosphorus, 1060, sulfur, oh, dips back down again. Okay. Then up to chlorine, 1255, and then argon's 1527. Okay. So the trend is that it gets higher as you go across that period on the table. But there's 2 places where it doesn't follow the trend. Dip. Yep.
So I know that you said that like between magnesium and aluminum it drops because that's going from group 2 to group 3. Is
That's
that
not the because, that's not why. It's just,
or I just mean
does.
like that's like the trend, but
So just like
technically isn't that group 13? Or because whenever you
It is, I'm sorry, yeah, 13. Yeah, that's an old number, yeah, 13, yep.
Okay, so it should be 2 and 13.
Yeah, 2 to 13, sorry.
Oh,
There. Yeah, that's actually group 13. Sorry.
oh, yeah.
Because 3 through 12 don't exist for rows 1, for rows 2 and 3. Sorry. Yeah. So you know the groups 1 to 18, right?
Yeah.
Sorry.
So does that exception stop happening whenever you get down into where the D block is?
Oh, no, it keeps going, but they don't ever ask about that.
Okay.
We're not either. It gets complicated. All right. So let's talk about why there's an exception. First off, let's talk about down the group trend that doesn't have any exceptions. Okay. Ionization energy decreases going down a group because that valence electron is further away from the nucleus. It's almost the same thing as the atomic radius. Okay.
Those ones with higher ionization energy like to be closer to the nucleus.
No, they don't like to be. They are.
They are, but
They don't like to be there at all, but that's where they're forced to be because they're being pulled by something. I'm related to something. So if we compare sodium to potassium, right? Okay. What we're talking about here is how much energy does it take to get rid of that electron right there, okay, versus this one right here. Everybody follow me? So we're trying to take this electron off, and we're trying to take this electron off. Which one's harder? Which one's easier? This one's harder to get rid of because it's closer to the nucleus. Okay. This one is easier because it's further away. All right. So this attraction between protons and electrons is based on a physics thing called Coulomb's law. Just put this right. Coulomb's law, okay? It says that attraction or repulsion, whichever one you're dealing with, okay? Increases with magnitude of charge and decreases the distance. There's an equation for this that's part of physics class, but not part of the chemistry class. Chemists just need to know the concept. Physics need to know the concept and actually do the math, okay? All right, but Coulomb's law says that attraction and repulsion is based off two things, okay? Number one, how much charge do you have? So that goes back to that that goes to your effective nuclear charge argument, okay? In our last example, 7 protons and electrons pulled on each other more than 6 did, right? 7 is more charged than 6, okay? All right. In fact, there's a total of 14 versus 12 if you take in the protons and the electrons, right? So the second part of Coulomb's law has to do with the distance. The further away things are from each other, the less they pull on each other. If you've ever played with magnets, you got a concept for that. Because magnets, magnetic attraction, repulsion, and electro attraction, repulsion are actually the same thing. Okay, in physics they are. In chemistry we keep them different, but they're the same thing. All right, and the closer you get a magnet together, the harder it is to keep them from either separating or pushing apart, depending on how your poles are. Right. So the 4s electron in potassium is easier to remove than the 3s electron in sodium because this is further away. There is a greater distance between the negatives and the positives.
Can you say what magnitude of charge is again?
The number of charges.
Oh.
Okay. Now, just so we don't think of it, just make sure we're thinking of this sort of correctly. We look at group 2. Let's just take magnesium and calcium. We're talking about ionization energy. We're normally referring to what we call the first ionization energy. You can see on this chart, there's a second, a third, a fourth, and a fifth. We'll get to that here in a minute. Then we'll get down to 49. That's good. So we'll get to that in just a minute. But first ionization energy, if we're comparing these two, okay, we're talking about this electron, that down spin electron right there, versus this down spin electron right here. Okay. How much energy does it take to take this guy off versus this one? It's going to be more to take this one off, right? Because magnesium, this electron is closer to the nucleus of magnesium than this one is to the nucleus of calcium. So they're more stuck to each other.
So using that, can you answer the question of why does ionization decrease down group without any exceptions? I can use that to answer that.
Do what now?
Why does ionization decrease down a group without any exceptions? Could I use that for that or no?
What is that?
Use what we just drew.
Yes.
as the-
Uh-huh. All right. Now let's talk about across a period, okay? And then we got to dig into these exceptions, okay? Which is going to be a fun conversation. All right, so going across the row, as we like to call them, across a period, it's going to increase because of the greater effective nuclear charge. Same reason they get smaller is the same reason it's harder to take the electrons off. Okay? Same reason. So what about the exceptions though? So the first exception happens between group 2 and 13. which is beryllium to boron, right? All right, so okay. According to the trend, not the exception, but according to the trend, which one of these we're talking about? This one versus this one, right? They're outermost electrons. The electrons come out in the opposite order that they go in. So according to the trend, which one of those is supposed to be the hardest to remove? Right? According to the trend, but not the exceptions, but according to the trend, increasing across a period, which one should be the hardest to remove? Do this, boron. Boron's got 5 protons, and beryllium has 4, right? So boron has a greater effective nuclear charge, and therefore, according to what we would think here, based off of that, this one is the harder one to remove. The trend says it increases going across a period, right? Beryllium to boron, it should get higher. The energy required should be higher, which means it's harder to remove it. Okay, it takes more energy, means it's harder to do. Okay, all right. But that's not true in reality. Okay, so here's why. This is a little bit wordy. The electrons do not penetrate the nucleus as far as s electrons do. Okay.
Can you say the question again? Like,
Not a question.
I know, like, this is, would you, we were talking
The
about.
explanation. This is the explanation for this exception.
Okay, so,
All right, look right here. This is a model of an s orbital. Okay. The nucleus is in the middle where these little metal rods all intersect. Okay. All right. This is the model of a p orbital. Okay. The nucleus is where the little rods intersect. If we say an electron is in an s orbital, like this electron right here is in an s orbital, that means there's a 90% chance it's somewhere inside that spherical ball, right? Which includes the nucleus of the atom. So it could be inside the nucleus, even though your middle school teacher told you the electrons were outside the nucleus, right? Okay. Not necessarily true. There's a chance, just as good a chance it's inside the nucleus as there is a chance it's out. Okay, it's somewhere in that spherical shape, maybe 90% chance. Okay, but a p electron, such as this one, can never be in the nucleus. That's what's called a node. Okay, mathematical terminology. Okay, there is a 0% chance that this electron is ever inside that nucleus. Because the orbital doesn't exist at the nucleus. It's got 2 parts to it, 2 lobes they're called. There's a 90% chance that that electron is somewhere in here or here. Not both, but we don't know which one. It's somewhere here, either here or here, but it's never there. Okay? So that's why we have this statement. P electrons do not penetrate the nucleus as far as S electrons do. S electrons can get really close and therefore get held really tight. Okay? P's don't. All right? So that makes this one harder to remove than this one. Trend says it's the other way around. Trend says this is the harder one to remove because it's further to the right on the table. But in reality, this one's harder to remove. Because on average, and based on probabilities, it's going to be closer to the nucleus, maybe even inside the nucleus. But that one is probably not closer and definitely never going to be inside.
So why does
That's
it
a
change?
complicated idea.
So why does it change back once it gets to the next one?
Because the next one is just, we're just comparing two peaks. So if we draw carbon up here, we're looking at this electron versus this one. You're comparing, so the comparison between boron and carbon is between a p electron and another p electron. Now we're back on ground now. So now the difference is carbon's got 6 protons versus 5, so carbon's already removed. So back, we're still breaking the exception. Until you get over to that 15 and 16. And then there's another little thing that happens. So when we have nitrogen and oxygen, okay, we're talking about the first ionization energy of nitrogen and oxygen. We're comparing the energy to remove that electron versus this electron. That's the two that we're comparing, okay? This one versus this one. The trend says this one should be harder to remove because 8 protons should be pulling harder on it than the 7 of nitrogen's pulling on that one, okay? But as we look at the actual data, we find that this one is easier to remove, not harder to remove. It breaks the trend, okay? This one's a simpler explanation. What are those 2 electrons right there doing to each other? Yeah, they're repelling each other. Now, they tolerate each other because they're spinning opposite directions, but they still don't like each other, right? So, yes, this one's being attracted by 8 instead of 7, but it's also being pushed by 1. It's closer to that 1 than it is those 8. So this other electron right here is basically trying to shove that guy out anyway. Okay? So this one is easier to remove, even though oxygen has a greater effective nuclear charge. Its outer electron is easier to remove because of the repulsion from that paired electron, and that's the statement we need to know. It's because of the repulsion of that paired electron. That's almost perfect timing. That was right. So we need to go home tonight and ponder this a little bit, okay? We will pick back up right here tomorrow.
And those 2 quizzes would be tonight.
Yeah. And we haven't had a grade in here yet. We need to do something. So we're gonna have a quiz Friday on something that we talked about up until today. Today is not on, okay? So probably electron configurations. Maybe, well, I'll tell you what, we've got
We could do that on David's
we've
Day.
got empirical formulas and electron configurations. That's our 2 big topics we'll have.
Let us start off strong.
No, please,
Please start off strong.
So we need to do empirical formulas.
What was the biggest factor?
Yeah, I mean, probably.
Please, let us start off strong.
That's what we were
Well, I hope
working
you
on.
do start off strong. Both of those are things we did last year.
But like electron
But
configuration is
empirical
easier,
formulas-
so pick.
No, it's not. Really? No, it's not.
Oh, no, it's
so much
very
harder.
difficult.
It's very hard.
It's
very
very
difficult.
difficult. Empirical formulas are too easy.
It's too easy. No.
It's too easy.
That's funny, honestly. It's too easy.
Well, I look at Miss Hayden.
Speaking of,
Hayden made it for me.
hey, that's not.
Alright, so let's just say quiz Friday, empirical formulas, or electron configurations.
Did you say or?
What would I gotta go back?
I'm almost at order of magnitude, electron configurations in general, so.
I can do
Like,
both.
complete and shortened?
Whichever one it asks you for. You should be able to do all.
Empirical form is percent composition and stuff, right?